All right, looking through the Frappy. So these are chapter 5, 6, and 7. So these three free response questions, AP style. So thinking about what do I need to drive home from each of these. Okay. This first one here is chapter 5. So it's probability. So thinking general probability, thinking addition rule, thinking multiplication rule, thinking conditional probability. Those are the things. All right. So here we go. We have this two-way table. Two-way tables are awesome way to just really coordinate everything that's going on here. First thing it says, what is the probability that a person chosen at random? So this is going to be important though. A person. Remember, because if it's multiple people, we're thinking multiply. But since it's a person, I'm thinking I just got to pick one, but I'm going to think about the different events that that one person can have, right? So that's going to be important as I work through this is understanding that word a person right there. Okay. So what's the probability that a person chosen at random from this sample will have moderate political views? All right, so let's look at this. So here's political views. These are the moderate political views. So we are going to take the 75 out of everybody, right? Because those are the people with moderate views. We didn't condition it at all. We just kept it that. So let's do that. So probability that a person will have moderate political views is going to be equal to 75 over 255, which then I'm just going to put in my calculator here, and I'm going to get 0.294. Right, so that would do it. It's roughly 29%, if that's the way you'd like to kind of categorize it. All right, so let me take those off so that way so I can come back and I can redo it. What's probably that? Here we go again. A person. So again, that idea, not multiplying, because I'm not talking about multiple trials. A person chosen at random from those in the sample work who are between the ages of 30 and 44 will have moderate political views. Okay, so let's try this again. Let's see what we got. So what is the probability that a person chosen at random from those in the sample who are between the ages of 30 and 44? So this, what they're saying right here, from those, we could give that another word and we can say, given that they are between the ages of 30 and 44, what's the probability that they will have a moderate political view? So here's how I would dial this in. Probability that you have a moderate political view given that you're 30 to 44 age range. Okay. Now doing this on a two-way table is nice because really we're just going to take this age group right here, 30 to 44. This is what's given. So we are locked into that row. So don't try to abandon the row now. We're going to go right in there. We're going to do the moderate view. So actually let me do this with a little bit different. Let's do the moderate view out of the total in that group, right? So that's really, it's 30 out of the 85. Now I could use my formula for conditional probability if I choose to, but you're going to get the same answer by pulling those certain values, 0.3529 in my calculator. So there you go. But that is a conditional statement. It's a conditional probability. So do know though, look how AP changes that word, and they don't explicitly just come out and say given. Okay, so here we go. Next one. Are your answers A and B are political views? Are they independent for the population of adults in the metropolitan area? Are they independent? Okay, so here's what we need to do. We need to find out, is the probability that your moderate given 30 to 44 age group, is it equal to the probability of being just a moderate political view? If that is true, then we need to also check, and we'll try the probability that you're the 30 to 44 age group given that you're moderate, and see if it's equal to the probability of a 30 to 44 age group. So if they are both true, then they are independent. Now, if one of those fails, then we are not independent, okay? So that's how that works, right? And that is one of the formulas we want to have written down, is this right here. It's essentially, is the thing with the given the same as the thing without the given, right? That's essentially it. Because then, if that is true, we know that we're on the path to independence, right? Because that given thing, does not affect the outcome. So this is pretty simple in the way that we're going to do this. We're going to go 0.03529 equals 0.294 because we've already done the work ahead. And guess what? Those actually are not equal to each other. So we are going to say not independent. And there's your answer. And this is the proof, right? You want to show that they are not equal to each other. There, right? So we do have that check for independence right there. And there you go. There is chapter 5. There was some probability. Now that's not all of chapter 5, but that is a free response problem. And I love that they gave us a two-way table. Two-way table really, really, really helps out with that. Okay, let's move on to chapter 6. Chapter 6 is discrete random variables, continuous random variables, binomial, and geometric, right? That's what we did in chapter 6. So right off the bat, right, this is my indicator. Check that out right there. That is a table of values. So if this is a table of values, then I know that this is a discrete random variable. All right, so that's nice. Whoa, that's not how you spell discrete. That's nice that we can recognize it as discrete. So then I can go to my formula sheets and I have all kinds of formulas, and it's easy to pick out values that I want over there. Okay. First one, compute and interpret the mean and standard deviation of R. So here's R over here. R represents the number of repairs, right? They're kind of telling you that right there. So if I need the mean of R, let's go look at discrete random variable, right? So this is where it's like gives the little outcome times probability, the summation of this. So this is what it's going to look like as I kind of start putting this together. First outcome is 0, probability is 0.4, plus the next outcome is 1 times its probability of 0.3, plus the next outcome is 2 times its probability of 0.2, plus the next outcome is 3 times its probability of 0.1. All right, and then we're going to get an answer. I'm going to do that here in just a second. And then I'm going to get standard deviation of R is equal to the square root of the summation of x minus its mean, that we just did, squared times its probability. And then we're going to keep that summation going, right? So this is kind of what it would look like. I'm only going to do part of this one, but I'm going to do 0 minus the mean squared times its probability 0.4, plus the next one, 1 minus the mean squared times its probability 0.3, plus dot, dot, dot. Yes, that is going to continue. I don't really want to continue it right now. Okay, so I do that. Let me just kind of jot down something real quick. 0, 1, 2, and 3, and we got what? 0.4, 0.3, 0.2, 0.1. Okay, so let's do this real quick. So I'm going to decide to go to staplet.com, and then I'm going to plug in this table, right? I'm going to go find the discrete, and then just have it calculate that. It's going to show me both a histogram, but also it's going to calculate for me. So I'm going to do that, and then I'll pop some answers in here. All right, now I'm back from Staplet, and I got this one. I plugged that in, and I got one, and I plugged that one, and I got one. And there you go. That's what I got. So that is, again, using formulas, right? These are on your formula sheet. You can go find them under the discrete random variable section. But I went ahead and used Staplet because Staplet is a nice place to get those done. You can also use your calculator. It takes a little bit longer to use your calculator. That's why I use Staplet a lot faster. All right, part B. Suppose we also randomly selected a phone that may require repairs over a lifetime. The mean and standard deviation of the number of repairs for the phone are 2 and 1.2 respectively. That means mean and standard deviation. Assuming the phones and the MP3 player break down independently of each other, compute and interpret the mean and standard deviation of the total number of repairs. So here's what we need. We got total is going to be equal to the repairs plus the repairs for this brand of phone. Let's call it this a phone, right? So R is going to be my what we just got finished looking at here, and that one's there. So here's what we know about expected value. Expected value of T should equal the expected value of R plus the expected value of the phones. Well, that's going to be pretty easy because the expected value R we already found out was 1. The expected value of the phones is 2. So 3. We'd expect 3 repairs total between these two. Standard deviation. Now recall, standard deviation, this is where it gets a little bit funky. We got a square root because we can't just take standard deviations and add them together. Remember, we have to change them to variance. So standard deviations squared creates variance. Add them together, and then square root them to get them back to where we want to be. All right, so I'm going to just do that real quick. So I'm going to get square root of 1 squared plus 1.2 squared, and then let's see what we get. So square root of 1 squared plus 1.2 squared, all under the square root. I get a 1.56. All right, there's our answers right here. So we would expect 3 total repairs between the two and have a standard deviation of 1.56 between the two. All right, keep moving along. Part C, each MP3 player repair costs $15 and each phone repair costs $25. Compute the mean and standard deviation of the total amount you can expect to pay in repairs over the lifetime. Okay, so here's what they're really getting us to do, is they want us to kind of combine a couple ideas here. One, let's go ahead and figure out what is the repair cost, right, for MP3, and then what is the repair cost for phone. So here's what we know is we're going to create a new, let's call it MP3 cost, MC, right? And that's going to be equal to $15 times the R, right? So however many repairs times 15 is going to give me the cost for MP3. The phone cost is going to be $25 for every phone repair, and we called that P earlier on, right? So let's go ahead and do these real quickly. So what is the expected value of the MP3 player cost? Well, we know that multiplying always affects the mean, so we're going to get a new mean here, which is going to be the old mean times 15. So we would expect $15 for repairs on the MP3 player. The expected phone cost, the mean, right, is going to be the old mean of phone, which is what, 2 times 25. So we would expect a $50 repair cost for phones, right? But now they each have standard deviation. So when we're thinking about cost, does multiplication affect standard deviation? Absolutely it does. So take the old standard deviation and multiply it by 15. So the old standard deviation, remember it was up here. I'm going to circle it. It's 1 up there. And the standard deviation for the phone cost. So does multiplication affect standard deviation? It sure does. So let's take 1.2. So I'm going to do this now. 1.2 times 25. So that's going to be $30 is our new standard deviation. All right, so that's just kind of doing what we call a linear transformation. But they said compute the mean of the total amount expected to pay. So the total cost is equal to the MP3 player cost plus the phone cost. Okay, well, the expected total cost is going to be pretty easy because we just add the expected cost of each of those together. And we have an expected total cost of $65. Standard deviation of the total cost is equal to, whoops, we got to do our formula again. We got to go standard deviation of the MP3 player cost squared, because you got to turn it to a variance. Standard deviation of the phone cost, you got to square that, change it to a variance. Now you can add them together. Then you got to square root them to get them back to where they should be. 15 squared plus 30 squared, all under the square root. Let's see what we get. I'm going to do this with my calculator. I'm going 15 squared plus 30 squared there. So that looks like we're going to get 33.54. And we're talking about money. Done. Okay. There you go. That's part C. So this is a discrete random variable, but really it focused heavily, right? I mean, this whole bottom part right here focused on the combinations and linear transformations that you can do within there. Okay, so definitely worth going back and looking at that part of your chapter 6, right? If you kind of got lost there. All right, let's finally go to chapter 7. Now, this is important because this sets us up for where we are going second semester. All right, so we got this thing right here, television producer, scheduled, advertiser. The lengths of the advertisement are, here's a keyword, normally distributed. They give us the population mean of 28 seconds and a standard deviation of 5 seconds. Okay, so that's really good. During each hour of the program, 45 minutes are devoted to the program, 15 set aside for advertising. That's just kind of giving us some ideas. To fill the 15 minutes, the producer, here's our key, right? Randomly selects 30 advertisements, right? So we're talking a sample of size 30 that was randomly selected. All right, so that's going to help us out here. So when it says describe, you should go back to the idea of socks. What are the socks? Of the sampling distribution. So of the sampling distribution of sample means for random samples of 30 advertisements. All right, so what does that mean? Well, we need to talk about what is the shape. And you need to be very explicit on how did that work, right? So the shape, I believe it's going to be approximately normal, right? Approximately normal. Now, why? I'm going to check. Why? Because n is equal to 30, so the central limit theorem kicks in. And it's important to put CLT there, right? That's going to be good for us. All right, the center. By going to my formula, by definition, we know that the center of this sampling distribution should equal the center of the actual true population, which they gave us was 28, right? And then we can, again, check. And that is because they took a randomly selected, right? So that's what that's for. Actually, you know what? I'm going to come back here just a minute because now that I'm looking at that, the shape is actually not approximately normal. Central limit theorem would guarantee approximately normal. It is actually normal. Why? Because they said the population was normal. So actually, I'm just gonna add this in here right here. I don't actually need the central limit theorem. I'm just gonna say pop is normal, right? Because if it is normal already, then my sampling distribution will take on that same shape. Now, if it's not normal, the central limit theorem guarantees that it will start to become approximately normal, right? So at that threshold of 30. Okay, I digress. Let's go back. Spread. What is our spread? Here we go. It should be equal to the actual population standard deviation divided by the square root of our sample size. So I'm going to do that in my calculator. 5 divided by the square root of 30. Looks like we're going to get 0.9129. That's where I'm going to round it there. 4 decimal places seems good and appropriate. But let me just check real quick. How does that work? Did I independently? Well, we don't know how many advertisements, so we're going to have to say all advertisements is greater than or equal to 300. So do they have at least 300 advertisements to choose from? We are going to have to make an assumption and hope that that is true, right? So we're going to call that assumption check, population normal, randomly selected. Good. So I think everything's going to work out here. This is the description of what we are working with here. Now, why do they have us do part A? Because they need us to do part B. If 30 advertisements are randomly selected, what's the probability that the total number needed to air them will exceed the 15 minutes available? Exceed means more than 15. Well, let's do this. Let's set up our curve, and it is important that you're showing some work here, right? 28 is the actual center of this thing. The length of advertisements are 28 seconds, right? And then what we need to do is take 15 minutes. So I'm going to take, because they're talking minutes and we're talking seconds here, right? So what we need to do is average. So if 30 advertisements are there, we need to average those down to, well, what is the average for any single advertisement, right? And because right now we have the expected that it's going to be 20, any advertisement is going to be 28 seconds. But if I took 30 advertisements over 15 minutes, right, and averaged those to, I just need to average them so that I see, like, what are we actually after here? So 15 minutes, let's turn 15 minutes into seconds. So 15 times 60 is 900 seconds. So I got 900 seconds over 30 advertisements. So how much per advertisement? So I'm going to take 900 divided by 30, and so roughly 30 seconds. So that's what they're asking. So what is the probability that we average to more than 30 seconds, right? Because if I average to more than 30 seconds, then we got problems with our advertising, right? So the expected is that every advertisement's going to average out to 28 seconds. But if we run to 30 seconds or above, exceed the 30-second mark, then we got problems. All right, so that's what we're after here. So we're going to go back and use the info that we've done up ahead, right? So we had this, and we know that it's normal. So normal 28. So now I'm just going to go ahead and finish this thing off. If I was requested to do a z-score, I would be in the habit of doing this, right? Just because on AP, it's better to put more correct stuff than it is to not. So that'd be 30 seconds minus 28 seconds divided by the standard deviation that we got, right? So it's that one right there. So we're going to get 2 divided by 0.9129. It looks like we're going to get a z-score of 2.19. Now again, z-score tells me how far I would have to travel in standard deviations to get to the value that I'm looking at. So I'm going to have to go 2.19 standard deviations to get to 30 seconds. And then at the end of the day, let's just do this. Probability that that's equal to. What am I actually going to write in here? I'm going to just show it on here so that you see what I'm doing. Normal CDF, lower bound, 30 seconds, upper bound, infinity. Mean is 28, and standard deviation is, I'm going to put in 0.92, right? And this is important to put in the one that we calculated. Don't put 5 in there because we're doing a sample of 30. We're not doing a single, right? Important there, okay? So let's do that. Distribution, normal CDF, my lower bound 30, my upper bound infinity or anything close, 28, and then 0.9129. Okay, I'm going to do that, and I get a probability of 0.01423 if you want to. So we'd say roughly a 1.4% chance. All right, that's the probability that you will exceed the 15 minutes available. So a very, very low chance that will actually happen to us. All right, so there you go. There are the 3 free response questions, one from Chapter 5, one from Chapter 6, one from Chapter 7.